Good morning everyone. I am G. Likita from CSIT. Today my IIT Techtalk concept topic of applied physics is design of quantum computing circuits. Let's know what is meant by quantum computing. The quantum computing is an emerging method of computation that promises to accomplish computational tasks and algorithms that are too difficult to perform on existing computing paradigms. Some of the promising applications of quantum computing includes number theory, encryption, search, and scientific computation. Circuits must be designed to apply quantum machines to these applications. This work introduces quantum circuit design. We provide a brief introduction to quantum computing and then we illustrate gates used in quantum circuit design. We conclude by introducing quantum circuits for arithmetic operations. The emerging computing paradigm of quantum computing shows promise due to its application in number theory, encryption, search, scientific computation, and image processing. 2 to 8 super polynomial factor computation speed increases have been found for many algorithms in these areas. In a quantum computer, information is encoded in novel ways such as electron energy levels or the spin state of an atomic nucleus. 10. A bit of information on a quantum machine is called a qubit, that is quantum bit. Quantum computers operate based on the principles of quantum mechanics. Defines several quantum mechanical properties relevant to quantum computation. By using these properties, we can achieve the fantastic speedups reported. However, the principles of quantum mechanics present unique challenges to the circuit implementation of these algorithms. A significant distinction from classical circuit design, that is CMOS, is that all quantum mechanical operations are unitary or reversible. Quantum circuit is composed of gates which represent quantum mechanical operations. Thus, all quantum circuits must have a one-to-one correspondence and be reversible. As a result, quantum circuit designers must use reversible gates and contend with additional resource codes such as auxiliary inputs or auxilia. In this work, we introduce the principles of quantum circuit design. We begin with introduction to reversible and quantum gates by presenting basic concepts such as logic gates often used in the design of quantum circuits. Then, in quantum arithmetic circuits, we present rudimentary quantum arithmetic circuits such as adders, subtractors. Unique quantum computer properties. Superposition. Here the superposition means the quantum machines are probabilistic systems. Thus a qubit is 1 with a probability p and 0 with a probability 1 to p. Entanglement. 2 or more qubits can become linked such that the state of one qubit is dependent on the other's. Measurement. For our purposes, how we determine the results of computation. After measurement, a qubit superposition state is collapsed into either 0 or 1 depending on the probability. Teleportation. Quantum states can be transmitted between locations. Requires a classical communication channel and entanglement. Decoherence. Over time, quantum states become corrupted due to such factors as environmental noise. For more details, the reader is encouraged to see the work. Reversible and quantum gates. First, reversible logical gates. To implement quantum algorithms, circuits based on quantum gates must be created. Due to the physical properties of quantum hardware, a quantum circuit will not lose information during computation and can be reversed. Important reversible gates are CNOT gate, the Toffoli gate, and the Fredkin gate are illustrated. Toffoli gate shows the schematic image of the Toffoli gate. The Toffoli gate is a 3 output reversible logic gate and has the mapping A B C to A B A B C. Let's see what are the basic reverse gates. Here the Toffoli gate is this, and this is the Fredkin gate. This is the CNOT gate. as these are the gates of the given. Next, the quantum circuit performance measures. Qubit cost, the total number of qubits required to design the quantum circuit. Gate count, the total number of gates used in the quantum circuit. Garbage outputs, any outputs which exist to preserve reversibility but are not primary inputs or useful outputs. Ancillary, all constant inputs to the quantum circuit. Depth, the number of gate layers in the circuit, where a layer consists of quantum operations that can be performed simultaneously. The Toffoli gate can realize many familiar logic operations such as AND, OR, and NAND with the appropriate combination of inputs. Second, let us know Franklin gate. The schematic image of the Fredkin gate or control swap gate, CS swap gate. The Fredkin gate is a 3-input, 3-output reversible logic gate that has the mapping A, B, C to A, B, A, B, A, C. The Fredkin gate can realize many familiar logic operations such as AND, OR, and NAND with the appropriate combination of inputs. The Fredkin gate also functions as a multiplexer. CNOT gate. The schematic image of the CNOT gate. The CNOT gate is a 2-input, 2-output reversible logic gate that has the mapping AB to AB. The CNOT gate can realize the XOR and XNOR operations with the appropriate combination of inputs. Quantum circuit resource cost measures. We define the resource measures often used to evaluate quantum circuits. Garbage output is a significant problem in quantum circuit design because these outputs must be cleared if the occupied qubits are to be used later. Removing these outputs doubles the circuit's gate count and adds to the total qubit cost. Qubit cost is an important design metric as existing quantum machines provide few qubits for computation. Depth is an important measure due to decoherence. Gate count and depth have become important performance metrics for fault-tolerant quantum circuits. Quantum arithmetic circuits. With the reversible gates introduced in the previous section, quantum circuits for implementing quantum algorithms can be created. We present quantum circuits for addition, subtraction, and multiplication. These can be used as building blocks to build larger quantum circuits for realizing algorithms. Figure presents how to read quantum circuit diagrams, such as shown in this work. Here is a figure to know how to read a quantum circuit. Quantum circuit for addition. Here is to know how the quantum circuit for addition is going on. It is an instance of the quantum addition circuit presented in work presented by Taplial and Ranganathnam 15 for the addition of 3 bits. Illustrates how the quantum addition circuit performs addition. Given two n-bit numbers A and B stored in quantum registers A and B, the register which keeps the value A at the end of commutation and the register with B will have the sum values Sn1 to S0. The most significant sum bit Sn is produced on a circuit is calculating 6 of 110 plus 3 of 011 plus 9 of 1001. These are the gate values. Here you can see what are the gates and what is the map or operations of quantum adder. Register A equals to 110 and B equals to 011. To see how the circuit performs addition, the circuit is divided into 5 stages with qubit values shown after each state and Celia Z set to 0. The quantum addition circuit calculates the sum of A and B by performing ripple carry addition. The quantum adder shown in this work saves resources compared to existing work. Quantum registers are typically presented using bracket notation, that is A and B. We avoid this notation for simplicity. Quantum circuit for conditional addition. Figure shows an example of the quantum conditional adder. Shows an example of the quantum conditional adder presented by Munoz, Corias and Talpial for the conditional addition of 3 bits. The quantum conditional adder is controlled by qubit control. When control equals to 1, the circuit performs addition. When control equals to 0, the inputs are unchanged. Thus, given two n-bit numbers A and B in quantum registers A and B, register B will have the sum S at the end of the computation when control equals to 1. Register B will keep the value B when control equals to 0. Register A will always be restored to the original value A. Here is the diagram for quantum arithmetic circuits. You can see the quantum arithmetic circuits structure. Quantum circuit for subtraction. The quantum subtractor presented by Taplial sized it for subtracting 3-bit values. The subtractor calculates B plus A, where B plus A equals to B minus A. Thus, given 2 and bits 2's complement numbers A and B in quantum registers A and B, register A will be restored to the original value A and the register B will have the difference D at the end of computation. By placing NOT gates on each element of register B before and after the adder, the new circuit calculates B plus A. The circuitry used to calculate the sum bit Sn can be removed from the quantum adder because the circuitry is not needed to be calculated B plus A. Quantum circuit for multiplication. Here we can know what is the quantum circuit for multiplication. That is it is presented by Munoz, Corias and Tapial, and the circuit provides an example how quantum arithmetic circuits can be combined to realize more complex circuits. Quantum conditional adders are needed to implement a quantum multiplier. We follow the design steps in the work by Munoz, Corias and Tapial to construct the quantum multiplier. The multiplier implements the shift and add multiplication algorithm and calculates the given formula. And the inputs A and B are stored in quantum registers A and B and restored to the original values after computation. The product of A and B will appear on 2n plus 1 set to 0. The summation in expression 1 is implemented using conditional adders and arrays of Toffoli gates. And the 2i shifts are performed without additional hardware. Conclusion. Here the conclusion and future directions are. This work introduces the emerging field of quantum circuit design. We present gates used to realize quantum circuits and present quantum arithmetic circuits that are constructed from these gates. Quantum circuits for addition, subtraction, conditional addition and multiplication are shown. Quantum arithmetic circuits are needed to design circuits to implement quantum algorithms. We conclude that the application of quantum information processing and quantum computing are important areas for promising future research explorations. Thank you.